Albert Einstein, a name synonymous with genius, forever altered our understanding of the universe. His theories of relativity stand as pillars of modern physics, unraveling the mysteries of gravity, space, and time. Einstein's revolutionary ideas challenged the very foundations of classical physics, established by giants like Isaac Newton. He unveiled a reality far more bizarre and counterintuitive than we could have ever imagined. Einstein's impact on science extends far beyond his equations. He inspired generations of scientists and ignited our curiosity about the cosmos. His work continues to shape our exploration of the universe, from the smallest particles to the largest structures. This essay will embark on a journey through the history of relativity, exploring its origins, principles, and profound implications for our understanding of the cosmos. Before we can delve into the intricacies of relativity, we must first understand the world before Einstein. For centuries, Isaac Newton's laws of motion and universal gravitation reigned supreme. Newton's universe was one of absolute space and time. Space acted as a rigid, unchanging backdrop against which objects moved, and time flowed uniformly for all observers. Newtonian physics provided an elegant and intuitive explanation for the motion of planets, the swing of pendulums, and everyday phenomena we observe on Earth. His laws were so successful that they fostered a sense of certainty in the scientific community. The universe seemed predictable, governed by immutable laws. However, as our understanding of the universe progressed, cracks began to appear in this seemingly perfect edifice. The 19th century witnessed the rise of electromagnetism, a force that governs the interaction between electrically charged particles. This era marked a significant turning point in the understanding of physical phenomena, as scientists began to unravel the mysteries of electric and magnetic fields. Scientists like Michael Faraday and James Clerk Maxwell made groundbreaking discoveries in this field. Faraday's experiments with electromagnetic induction and Maxwell's theoretical insights laid the foundation for modern electromagnetism. Maxwell's equations, a set of elegant mathematical expressions, unified electricity, magnetism, and light. These equations not only described how electric and magnetic fields interact but also predicted the existence of electromagnetic waves. These equations predicted that light travels at a constant speed, an astonishing revelation that contradicted Newtonian physics. This constant speed of light became a cornerstone in the study of electromagnetism and led to further scientific inquiries. According to Newtonian physics, the speed of light should change depending on the motion of the observer or the source of light. This was a widely accepted notion before Maxwell's groundbreaking work. However, Maxwell's equations suggested otherwise, implying that the speed of light is absolute, independent of the observer's motion. This was a radical departure from the classical understanding of physics. This discrepancy led to the hypothesis of the luminiferous ether, a hypothetical medium through which light waves were thought to propagate. Scientists believed that this ether was necessary to explain how light could travel through the vacuum of space. The ether was envisioned as a universal frame of reference against which the speed of light could be measured. This concept dominated scientific thought until the early 20th century when new theories began to challenge its existence. In 1905, a young patent clerk named Albert Einstein published a paper that would forever change the course of physics. This year, often referred to as Einstein's Annus Mirabilis or Miracle Year, saw him produce 4 groundbreaking papers, each of which would have been enough to secure his place in history. This groundbreaking work, titled On the Electrodynamics of Moving Bodies, introduced his theory of special relativity. It was a radical departure from the classical mechanics that had dominated physics since the time of Newton. Einstein's genius lay not in conducting complex experiments but in his profound thought experiments and elegant mathematical reasoning. He had an uncanny ability to visualize complex physical phenomena and translate them into simple yet powerful mathematical equations. At the heart of special relativity lie 2 deceptively simple postulates. These postulates would go on to challenge and ultimately reshape our understanding of space, time, and energy. First, Einstein asserted that the laws of physics are the same for all observers in uniform motion. This principle of relativity was a bold statement that unified the laws of mechanics and electromagnetism. This means that the results of any experiment should be identical whether you are standing still, moving at a constant speed in a straight line, or on a train traveling at a uniform velocity. It was a revolutionary idea that defied the conventional wisdom of the time. His second postulate, the most revolutionary, stated that the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source. This constancy of the speed of light would lead to profound implications, including the famous equation E=mc², which revealed the equivalence of mass and energy. Section 5. Time and Space Redefined. Implications of Special Relativity. Einstein's postulates, while seemingly straightforward, led to mind-boggling consequences that shattered our intuitive understanding of space and time. Special relativity revealed that time and space are not absolute but relative, meaning that they depend on the observer's frame of reference. One of the most startling implications of special relativity is time dilation. This phenomenon dictates that time slows down for objects in motion relative to a stationary observer. Another consequence is length contraction, which states that objects in motion appear shorter in the direction of their motion relative to a stationary observer. These effects become more pronounced as objects approach the speed of light. Section 6. Beyond Special Relativity, the Quest for a Universal Theory. While special relativity revolutionized our understanding of space and time, it had limitations. It only dealt with inertial frames of reference, those moving at constant velocities. Einstein realized that his theory was incomplete, as it could not account for gravity, a force that governs the motion of objects with mass. Einstein embarked on a quest to develop a more comprehensive theory that could incorporate gravity into the framework of relativity. This intellectual pursuit lasted for over a decade, marked by periods of intense contemplation and groundbreaking insights. He sought a theory that could explain the behavior of objects not only in inertial frames but also in accelerating frames and under the influence of gravity. Section 7. Curving Reality Introducing General Relativity. In 1915, Einstein presented his theory of general relativity, a masterpiece that forever changed our understanding of gravity. General relativity is not merely a theory of gravity, it is a theory of space-time itself. Einstein's central idea was that gravity is not a force acting at a distance, but a manifestation of the curvature of space-time. Imagine a bowling ball placed on a trampoline. The ball's mass causes the trampoline to sag, creating a curvature. Similarly, massive objects in space warp the fabric of space-time around them. This curvature dictates how objects move in the presence of gravity. Instead of traveling in straight lines, objects follow the curves in space-time created by massive objects, like planets orbiting a star. Section 8. Experimental Triumphs. Validating Einstein's Masterpiece. General relativity, while mathematically elegant, needed experimental verification. Einstein's theory predicted several phenomena that differed from Newtonian predictions, providing opportunities to test its validity. One of the earliest and most dramatic confirmations came during the solar eclipse of 1919. General relativity predicted that the path of starlight passing close to the sun would be bent due to the sun's gravity. During a solar eclipse, when the sun's light is blocked, astronomers could observe the apparent shift in the position of stars near the sun's edge. The 1919 eclipse expedition led by Sir Arthur Eddington confirmed this prediction, providing compelling evidence for Einstein's theory. Section 9. The Universe in a Nutshell. A Journey Through Relativity and Beyond. This section takes us on an incredible journey through the mind-bending concepts of relativity and beyond, as envisioned by the legendary physicist Albert Einstein. This essay has merely scratched the surface of Einstein's revolutionary theories of relativity. His work fundamentally changed our understanding of space, time, and the very fabric of the universe. In The Universe in a Nutshell, we delve deeper into the fascinating consequences of these theories, exploring black holes, the enigmatic regions of space where gravity is so strong that not even light can escape. We also examine the expansion of the universe, a phenomenon that suggests the cosmos is continuously growing, and the intricate nature of space-time itself, which combines space and time into a single interwoven continuum. Einstein's work continues to inspire scientists today, driving our quest to understand the most profound mysteries of the cosmos. Researchers around the world are building on his theories, pushing the boundaries of what we know. I encourage you to explore the wonders of relativity further by reading The Universe in a Nutshell. This book offers a comprehensive yet accessible look at these complex ideas, making them understandable to everyone. It will take you on a captivating journey through the cosmos, revealing the elegance and beauty of Einstein's masterpiece. You'll gain a deeper appreciation for the universe and our place within it. Join us as we unravel the secrets of the universe and expand our understanding of our place within it. Together, we can explore the vastness of space and the incredible phenomena that govern it, continuing the legacy of curiosity and discovery.